Look up at the night sky, at that familiar tapestry of stars and planets, and you might feel a sense of cosmic comfort, a belief that we have our solar system mostly figured out. We learned the order of the planets in school. We've seen the photographs from robotic explorers, and it all seems so established. But what if that sense of familiarity is an illusion? What if everything we thought we knew about our own cosmic neighborhood, the very place we call home in this vast galaxy, was profoundly, spectacularly wrong? The truth is, our solar system is not a static museum of well-behaved orbs following simple rules. It is a living, breathing, and utterly bizarre arena of wonders that continuously defies our expectations and redefines the possible. With every new mission, with every powerful telescope pointed skyward, we are peeling back the layers of a reality far stranger and more magnificent than we ever dreamed. This isn't just about finding new rocks or mapping new craters. It's about confronting mysteries that challenge the very foundations of our understanding of physics, chemistry, and the nature of life itself. We are living in a golden age of discovery, where the script of our solar system's story is being rewritten before our very eyes, and what we are learning is more incredible than any work of science fiction. It's a journey that takes us from the scorching surface of Mercury to the icy, hidden oceans at the edge of our celestial domain, and it reveals a cosmos brimming with secrets waiting to be unlocked. Today, we embark on that journey together, a voyage into the unknown corners of our own backyard. We will count down 25 of the most bizarre, mind-bending, and outright shocking discoveries ever made within our solar system. These are not just curiosities for scientists in lab coats. They are revelations that speak to a universe of infinite complexity and wonder, a place where diamond icebergs float in liquid methane seas, where volcanoes spew frozen water into the vacuum of space, and where forces we cannot yet explain sculpt worlds in ways that seem to break all the rules. So prepare to have your perception of reality shifted. Prepare to question what you know, to feel that childlike sense of awe rekindled, and to see the familiar planets in a light you never thought possible. This is more than a list. It is an exploration of the greatest unsolved mysteries happening right on our cosmic doorstep, and you are invited to be part of the discovery. And so we begin our countdown at number 25 with a discovery that looks like something from a cosmic art gallery rather than a planet's atmosphere. High above the North Pole of Saturn, a perfect colossal hexagon spins, a geometric wonder etched into the clouds. This is not a fleeting storm or a temporary feature. It is a permanent, staggering structure, a six-sided jet stream that has endured for decades, perhaps even centuries. To truly grasp its scale, imagine a shape so vast that the entire Earth could fit inside it with room to spare. This is a weather pattern of almost impossible precision, a polygon of hurricane-force winds whipping around a central vortex, and its very existence challenges everything we thought we knew about the chaotic, turbulent nature of gas giant planets. We expect to see swirling, unstructured cyclones and anticyclones, not a figure from a geometry textbook writ large across the sky. The explanation for this atmospheric marvel lies in the complex dance of fluid dynamics. One leading theory suggests it's a manifestation of a phenomenon known as a standing wave. Picture a wave like the one you might create by sloshing water in a bucket, but on a planetary scale. On a spinning sphere like Saturn, the complex interplay of atmospheric currents and the planet's own rotation can potentially trap such a wave, locking it into a stable, polygonal shape. The hexagon is essentially a persistent, self-reinforcing pattern in the fast-flowing jet stream, a visual representation of the physics playing out in that alien environment. What makes this even more compelling is that it's not just a flat image. Recent data reveals that this hexagonal wave extends hundreds of kilometers down into Saturn's atmosphere, a towering structure of layered weather. This bizarre feature serves as a powerful reminder that the laws of physics can produce outcomes of stunning order and beauty, even within the most violent and chaotic of environments. It's a natural masterpiece, a puzzle carved into the clouds of a distant world, reminding us that there are fundamental processes at work in our solar system that we are only just beginning to comprehend. While Saturn's hexagon presents a beautiful mystery of atmospheric physics, our next discovery shifts the search from stunning order to the tantalizing possibility of life itself. Journey with me from the cloud tops of the gas giant to one of its most unassuming moons, a small, icy world named Enceladus. For decades, it was little more than a speck of light in a telescope, a frozen marble orbiting its planetary parent. Then the Cassini spacecraft arrived, and it revealed a secret that sent shockwaves through the scientific community. Cassini's instruments detected something impossible: enormous geysers blasting from the moon's south pole like celestial fountains. These weren't just wisps of gas, they were colossal plumes of water vapor and icy particles, erupting with such force that they created one of Saturn's faint outer rings, the E-ring, essentially a donut of material fed by the eruptions of this tiny moon. The implications were staggering. Here was a world barely 300 miles across, small enough to fit inside the state of Arizona, actively spewing its internal contents out into space. Further analysis revealed the plumes were far more than just water. They contained a cocktail of simple organic compounds, the chemical building blocks essential for life as we know it. But the real breakthrough came when scientists deduced the source of these incredible geysers. The plumes were not shooting up from isolated, near-surface pockets of water. They were the visible sign of a vast, global ocean of liquid water, trapped between the moon's rocky core and its icy crust. This wasn't a local lake, it was a planet-wide sea hidden beneath a shell of ice. The mechanism that powers this incredible system is tidal heating. Enceladus doesn't orbit Saturn in a perfect circle. Its path is slightly elliptical, which means the immense gravitational pull of Saturn flexes and squeezes the moon's interior as it moves closer and farther away. This constant kneading generates enough friction and heat to keep that enormous subsurface ocean from freezing solid, and it creates immense pressure that forces the water up through cracks in the icy shell at the South Pole, where it explosively vents into the vacuum of space. This transforms Enceladus from a frozen relic into one of the most promising places to look for life beyond Earth. We now know it has liquid water, a key ingredient. We know it has a source of chemical energy from the hydrothermal vents likely active on its seafloor, mixing with the rocky core, and we know it has those complex organic molecules. It possesses the holy trinity of habitability, water, chemistry, and energy. The fact that this ocean is actively communicating with the surface, spraying its contents out into space for any passing spacecraft to sample, is nothing short of a miracle for astrobiologists. It means we don't need to drill through miles of ice to search for life. We can simply fly through the plume and analyze it. This tiny, brilliant world, shining in the distant sunlight, has fundamentally rewritten the rules of where life could potentially arise, proving that even in the cold, dark reaches of the outer solar system, environments rich with potential can thrive. But if you think a tiny moon like Enceladus is the only place hiding a secret ocean, prepare to be astonished by a world that takes this concept to a breathtaking extreme. At number 23, we travel to Jupiter's mesmerizing moon, Europa. Seen from a distance, it looks like a perfect, smooth marble, crisscrossed with a web of dark lines, gleaming as one of the brightest objects in the solar system. But this serene appearance is a cosmic illusion. Up close, Europa is a world of fractured, chaotic beauty, a globe-spanning jigsaw puzzle of ice. This isn't a dead, frozen ball. It is a geologically active world where the very ground beneath your feet is constantly being broken apart and remade. The most startling features are the vast regions scientists call chaos terrain. Imagine a frozen lake during a spring thaw, where massive sheets of ice have broken apart, tipped on their sides, and then refrozen into a jagged, disorganized mosaic. Now scale that image up to cover areas the size of entire cities. That is the reality on Europa. These chaotic zones are not simple cracks. They are places where the icy crust has been utterly shattered, with huge blocks, some the size of skyscrapers, tilted, rotated, and seemingly floating in a matrix of younger, refrozen ice. It looks like a planetary surface that has been through a blender and then hastily put back together. The driving force behind this incredible geological activity is once again a global ocean. But Europa's ocean isn't just a layer of water. It is a massive body, estimated to contain more than twice the volume of all Earth's oceans combined, all sealed beneath an ice shell that might be 10 to 15 miles thick. The constant gravitational tug of war from Jupiter and its other large moons creates intense tidal forces, flexing and heating Europa's interior in the same way Saturn warms Enceladus, but on a far grander scale. This internal heat keeps the ocean liquid and likely drives powerful currents and potentially even hydrothermal vents on the seafloor. The chaos terrain is the visible surface signature of this hidden, dynamic water world. Scientists believe these features form through a process of ice tectonics. The outer shell is not a single, solid piece, but a series of plates that shift and grind against each other. Heat from the ocean below melts the base of the ice, creating vast, shallow lakes suspended within the ice shell itself. When these subsurface lakes become overpressurized, the ice above them can collapse, shattering into the chaotic patterns we observe. In some models, plumes of warmer water from the ocean below might even punch through the ice, causing it to disintegrate and reform. This means the surface of Europa is in a constant, if slow-motion, conversation with the ocean beneath. Material from the deep might be carried upward and frozen into the new ice, while radiation from Jupiter's intense magnetic field bombards the surface, potentially creating oxidants that could, in turn, be cycled back down into the ocean. This entire cycle transforms Europa from a simple water-bearing moon into a complex, interconnected planetary system. The existence of its chaos terrain is our strongest evidence that this world is not just a candidate for life, but a prime one. It suggests an environment where energy, water, and the essential building blocks of chemistry are constantly being mixed and exchanged between the surface and the depths. A future mission descending to one of these fractured, icy plains wouldn't just be landing on a barren world. It would be stepping onto the frozen roof of a realm that could very well be home to the first alien life we ever find. Leaving the fractured, icy plains of Europa behind, we arrive at a world that feels at once strangely familiar and utterly alien. A place that holds the unique distinction of being the only other body in our solar system with liquid actively flowing on its surface. Welcome to Titan, Saturn's largest moon, a golden hazed world shrouded in mystery. For centuries, astronomers could only see it as a fuzzy orange dot, its surface completely hidden by a thick, smoggy atmosphere. That all changed when the Cassini-Huygens mission pierced that veil, revealing a landscape that was both breathtaking and profoundly disorienting. Titan is a place of bewildering contradictions. It has rivers that carve meandering channels, it has great lakes and seas that stretch for hundreds of miles, and it has clouds that drop rain, creating a dynamic weather system. But this is not the water-based world we know. On Titan, the liquid that defines the landscape is methane. The temperatures there are so cold, hovering around -290 degrees Fahrenheit, that water is frozen solid, harder than granite. In this deep freeze, methane and ethane, which are gases here on Earth, take on the roles that water plays in our own environment. They exist as liquids, filling vast basins and flowing across the surface in a complete, albeit alien, hydrological cycle. The Cassini spacecraft's radar maps unveiled this bizarre reality in stunning detail, showing dark, smooth patches that could only be bodies of liquid, nestled among brighter, rugged highlands. The Huygens probe, which descended through the hazy atmosphere and landed on the surface, sent back images of a landscape that looked eerily like a wet, rocky shoreline on Earth, complete with rounded pebbles that had been smoothed by the flow of liquid methane. We now know that Titan hosts seas like Kraken Mare, a body of liquid larger than North America's Great Lakes, and Ligeia Mare, where Cassini even observed a mysterious, disappearing feature nicknamed the Magic Island, a potential transient phenomenon like a rising bubble or a wave. This creates a world with a geology that mirrors Earth's in form, but is composed of entirely different materials. Imagine standing on the shore of one of these methane seas under a dim, orange sky. You wouldn't see crashing waves of water, but rather slow, viscous waves of hydrocarbons lapping against a shoreline of water ice bedrock. The rain that falls from the sky isn't made of water droplets, but of liquid methane, and it likely falls infrequently, perhaps in great torrential downpours that carve the river channels we see, followed by long, dry periods. The entire landscape is shaped by these exotic fluids, creating dunes not of sand, but of complex organic particles that snow out of the atmosphere, and mountains made of solid water ice that acts as the bedrock of this entire world. What makes Titan so compelling, beyond its bizarre beauty, is that it represents a second, independent example of many of the processes we consider essential for a habitable world, just with a different chemistry. It has a complex atmosphere, a liquid cycle, and a geologically active surface. It also possesses an immense internal ocean of liquid water, much like Europa and Enceladus, hidden deep below its icy crust. This means Titan is a world of two potential habitable zones, the subsurface water ocean and the unique hydrocarbon-rich surface environment. While it is far too cold for life as we know it to exist in the methane lakes, the complex organic chemistry occurring in its atmosphere and on its surface, chemistry that creates molecules called tholins, which give Titan its orange color, is the kind of probiotic chemistry that could have been a precursor to life on the early Earth. Studying Titan is like taking a time machine back to our own planet's infancy, offering us a chance to see how the building blocks of life might form and interact in a completely different environment. It is a living laboratory for organic chemistry, a world that holds up a distorted, frozen mirror to our own home, challenging our definitions of what makes a world Earth-like and expanding our understanding of where life could potentially get a start. If you thought the hidden oceans of Europa or the methane seas of Titan represented the outer limits of geological activity, then prepare to meet a world that exists in a state of pure, unrelenting fury. Our journey now takes us to Jupiter's innermost large moon, Io, a place that makes even the most violent volcanoes on Earth look like gentle campfires. Io holds a stark and dramatic title. It is, without question, the most volcanically active body in the entire solar system. This is not a world with occasional eruptions. It is a world that is eruption. Its surface is a constantly shifting canvas of fire and brimstone, dotted with hundreds of active volcanoes, some of which blast plumes of sulfur and silicate rock hundreds of miles high, so powerful they can be seen from telescopes across the vast gulf of space. These immense fountains of material fall back to the surface, painting the landscape in a spectacular, psychedelic palette of yellows, oranges, reds, and whites, a result of the various allotropes or forms of sulfur cooling at different temperatures. The entire moon is essentially being resurfaced right before our eyes, with fresh lava flows and new layers of volcanic debris burying any evidence of impact craters almost as soon as they form. In fact, Io's surface is so young, geologically speaking, that it's estimated to be completely remade every few million years, a blink of an eye on the cosmic timescale. The driving force behind this infernal spectacle is not the radioactive decay of elements in its core, as is the primary heat source for Earth's volcanoes, but something far more dramatic and relentless. Io is caught in an extraordinary gravitational tug-of-war between the colossal mass of Jupiter on one side and the rhythmic pulls from its sister moons, Europa and Ganymede, on the other. This orbital dance is not perfectly circular. Io is constantly being stretched and squeezed as its distance from Jupiter changes. Imagine taking a ball of clay and repeatedly kneading it in your hands. The internal friction generates heat. Now apply that concept to an entire world, with the gravitational hands of a gas giant and its large moons doing the kneading. This process, known as tidal heating, generates a truly staggering amount of internal energy, melting Io's rocky interior into vast global magma oceans. The solid crust we see, which is mostly composed of sulfur and silicate rock, is just a thin, brittle shell floating atop this churning, molten inferno. The pressure from below constantly seeks release, fracturing the crust and bursting forth in the hundreds of volcanic vents and calderas that define this tortured moon. The sheer intensity of this heating is almost incomprehensible. Io releases about 100 times more volcanic heat than all the active volcanoes on Earth combined. This creates features that dwarf their terrestrial counterparts, like Iapetus, a lava lake so vast it could swallow the entire state of New Jersey, its surface continuously overturning in a roiling, incandescent cauldron. Another volcano, Peel, consistently ejects an umbrella-shaped plume that reaches over 200 miles into the thin atmosphere, a permanent fixture of violence against the blackness of space. This relentless activity also gives Io a tenuous and constantly replenishing atmosphere, made mostly of sulfur dioxide, which is quickly stripped away by Jupiter's powerful magnetic field, creating a giant, donut-shaped torus of ionized gas that follows Io in its orbit. This world is a stunning, real-time demonstration of celestial mechanics in its most extreme form, a vivid testament to how orbital dynamics can literally shape and power a world, turning it into a crucible of cosmic fire. Leaving the volcanic fury of Io behind, we venture out to the quieter, colder reaches of Saturn's domain to encounter a moon that presents one of the most visually striking and long-standing mysteries in our solar system. Meet Iapetus, a world of two faces. Imagine a cosmic yin-yang, a sphere so perfectly divided between light and dark that early astronomers, when they could see it at all, were utterly baffled. One hemisphere of this moon is brilliantly white, gleaming with the reflectivity of fresh snow, while the opposing hemisphere is stained a deep, almost black charcoal gray. This isn't a subtle gradient, it's a stark, shocking line of demarcation, as if some celestial painter carefully dipped half the moon in ink. For centuries, the nature of this two-toned world was pure speculation. The pioneer of the telescope, Galileo Galilei himself, noted that Iapetus seemed to vanish and reappear as it orbited Saturn, visible only when its bright side was facing Earth. We now know this bizarre appearance is the result of an extraordinary cosmic balancing act, a feedback loop of heat and ice that has created one of the most dramatic surface contrasts anywhere we've looked. The leading theory that explains this phenomenon is as elegant as it is strange, a process known as thermal migration. It begins not with Iapetus itself, but with another, more distant and irregular moon of Saturn called Phoebe. Phoebe is a dark, captured object, likely a former denizen of the Kuiper belt, and it orbits Saturn in the opposite direction to most of the other moons, a celestial rebel. As it travels, it is constantly bombarded by micrometeoroids, which chip away at its surface, releasing a steady, faint stream of dark, dusty debris. This dust slowly spirals inward toward Saturn and drifting right through the orbital path of Iapetus. Because Iapetus is tidally locked, meaning the same hemisphere always faces forward in its orbit, that leading side acts like a giant windshield on a cosmic highway, collecting a continuous rain of this dark material over billions of years. This is the initial coating, the first stroke of the painter's brush, but this is where the process transforms from simple collection into a self-amplifying cycle. The dark material now settled on the surface of Iapetus has a crucial property. It is much less reflective than the pristine water ice that makes up the bulk of the Moon. A darker surface absorbs more sunlight, and absorbing more sunlight means it gets warmer. On a world as cold as Iapetus, even a slight increase in temperature is enough to trigger a monumental change. The water ice adjacent to and underneath this dark coating begins to sublimate. That is, it turns directly from a solid into a gas, skipping the liquid phase entirely in the vacuum of space. This water vapor then drifts across the Moon's surface, seeking colder ground. It eventually condenses and refreezes on the brighter, colder areas, particularly the trailing hemisphere and the poles. This process of deposition makes the bright areas even brighter and more reflective. And as the bright areas get brighter, they get colder, further enhancing their ability to attract and trap more water ice. Meanwhile, the now exposed darker areas, having lost their covering of ice, become even darker and more effective at absorbing heat, which in turn drives off even more of the surrounding ice. This creates a powerful runaway feedback loop. The initial sprinkling of dark dust essentially triggers a planetary-scale purification process where the Moon actively segregates its own materials, pushing its water ice to one side and concentrating the dark grime on the other. The result is the breathtaking dichotomy we see today. Adding to the strangeness is a colossal ridge that runs along the equator of the dark hemisphere, a mountain chain that stretches for over 800 miles and in some places towers over 12 miles high, making it one of the tallest features in the solar system relative to the size of the body it's on. In some sections, this ridge gives Iapetus the uncanny appearance of a giant walnut. The origin of this ridge remains an active debate. It could be frozen debris from a ring system that once circled the Moon and collapsed, or it might be the result of an ancient, short-lived burst of extreme tectonic activity that squeezed the Moon's equator, forcing material upward. Regardless of its origin, the equatorial ridge stands as a monumental landmark on a world already defined by its extreme duality. Iapetus is a stunning demonstration of how a simple initial condition, a sprinkling of foreign dust, can, through the unforgiving logic of physics, spiral into a global transformation, creating a world of two starkly different identities forever locked in a single spinning sphere. From the stark duality of Iapetus, we now turn our attention inward to the scorching, sun-blasted world of Mercury. It's a planet we often picture as a static, cratered relic, a place where all major geological activity ceased billions of years ago. But recent discoveries have shattered that quiet image, revealing a world that is surprisingly dynamic, still changing and settling in ways we never anticipated. Thanks to the incredible data sent back by NASA, a messenger spacecraft which became the first probe to orbit this tiny world, we now know that Mercury is a planet in motion. It is literally shrinking. The evidence for this lies in breathtaking, continent-sized features known as lobate scarps. Imagine a colossal cliff, not formed by erosion or water, but by the planet itself cracking and compressing under immense force. These scarps are essentially giant wrinkles on the face of Mercury, looking like a vast, crumpled piece of paper on a planetary scale. They can stretch for hundreds of miles and soar over a mile high, making them some of the most prominent tectonic landforms in the entire solar system. Their lobate or curved shape tells a specific story. They are thrust faults where one section of the planet's crust has been pushed up and over another, a clear sign of global contraction. For a planet to develop these kinds of features, its interior must be cooling down. Like a baked apple shrinking as it cools, Mercury's metallic core has been slowly solidifying over billions of years. As the core cools, it contracts and the entire planet follows suit, compressing the rocky outer mantle and crust. Since the crust has nowhere to go but inward, it has to accommodate the planet's decreasing volume. The only way it can do this is by breaking, thrusting large segments of rock upward and over one another, creating these monumental scarps. What makes this discovery so revolutionary is that MESSENGER didn't just find ancient scarps. It found small, fresh-looking ones that cut directly across and distort younger impact craters. This indicates that the process of planetary contraction didn't just happen in the distant past. It is almost certainly still happening today in a geological sense. This ongoing activity completely upends our traditional view of small, rocky planets. We used to think that worlds like Mercury and our Moon cooled off quickly after their formation, becoming geologically dead soon after the heavy bombardment era. Mercury's continued shrinkage tells us that its thermal engine is still running, albeit slowly. It forces us to reconsider the timelines of planetary evolution and the internal dynamics of all terrestrial worlds. The fact that we can see the tangible evidence of a planet changing size right now serves as a powerful reminder that our solar system is not a still life painting, but a living, breathing, and ever-changing system of worlds, each with its own unique and active story to tell. But while Mercury shrinks in near-permanent sunlight, our next destination offers a spectacle of a different kind of planetary transformation, one that unfolds not over eons, but in a matter of weeks, engulfing an entire world in a tempest of dust. We now arrive at the red planet Mars, a place of stark beauty and profound mystery, home to a phenomenon so immense it defies earthly comparison, the global dust storm. Imagine a storm that doesn't rage for a day or a week, but for months on end. A storm that doesn't cover a region or a continent, but spreads across the entire planet, rendering national borders and geographical features meaningless. This is not a localized weather event. It is a planet-wide climate catastrophe, a roiling ochre haze that rises from the surface and climbs dozens of miles into the thin atmosphere, eventually encircling the entire globe and blotting out the sun. These epic storms are a unique and recurring feature of the Martian climate cycle, typically occurring during the southern hemisphere's summer, when Mars is closest to the Sun in its elliptical orbit and receiving a burst of extrasolar energy. This influx of heat creates stronger temperature gradients, which in turn generate powerful winds that sweep across the arid, dusty plains. It often begins with a single, localized dust storm, perhaps in a vast basin like Hellas Planitia, one of the largest impact craters in the solar system. Under the right conditions, this small storm can act as a seed. The dust particles lifted into the atmosphere absorb sunlight, heating the air around them. This warmer air rises, sucking in more air from the surrounding regions, which then also begins to lift dust, creating a self-sustaining positive feedback loop. The storm begins to feed on itself, growing in size and intensity until it becomes a regional behemoth. And if the conditions are just right, and they are every few Martian years, these regional giants can merge, their outflow boundaries colliding and triggering new updrafts until the entire planet is enveloped in a single shroud of fine, suspended dust. The effect from orbit is both majestic and terrifying. Cameras on satellites like NASA Mars Reconnaissance Orbiter have watched as familiar landmarks, the vast canyons of Valles Marineris, the towering summit of Olympus Mons, simply vanish, swallowed by a featureless tan-colored veil. From the surface, the experience is even more profound. The rovers have been our eyes on the ground for these events. During the Great Global Storm of 2018, the Opportunity rover, which relied entirely on solar power, watched as the sky grew darker and darker. The tau, a measurement of atmospheric opacity, skyrocketed. What was once a clear, albeit thin, atmosphere became so thick with dust that it blocked over 99% of the direct sunlight. For Opportunity, it was a death sentence. Its solar panels could not generate enough power to keep its systems from freezing in the bitter Martian night, and after 15 years of trailblazing exploration, it fell silent, a victim of the planet's most extreme weather. The more nuclear-powered Curiosity rover, however, survived and provided an incredible frontline report. It witnessed daytime turn to an eerie, perpetual twilight. The sun was reduced to a faint, diffuse glow, and temperatures at the surface actually rose because the high-altitude dust was acting like a giant planet-wide blanket, trapping what little heat there was. This complete alteration of the atmospheric structure is one of the most significant impacts of these storms. They don't just block sunlight, they fundamentally reshape the Martian climate for months, shutting down the normal cycles of wind and weather and creating a temporary, single-cell global atmosphere. For future human explorers, these storms represent one of the greatest challenges. While the winds on Mars are fast, the atmosphere is so thin that they don't carry the destructive force of a hurricane on Earth. You wouldn't be knocked over by the wind itself. The real danger comes from the dust. This isn't like earthly sand. It's an incredibly fine, electrostatic powder, as abrasive as ground glass, and it would get into everything: seals, joints, airlocks, and machinery. It would coat solar panels, crippling a base's power supply, and it would pose a severe risk to human health if inhaled, potentially containing toxic perchlorates. A crew on the surface during a global storm would be effectively trapped inside their habitat for months, living under a perpetual, suffocating dusk, completely reliant on robust power and life support systems. Understanding and predicting these colossal events is not just an academic exercise. It is a critical step for any serious plan to establish a prolonged human presence on the red planet, a stark reminder that the challenges of space exploration are as much about surviving the environment as they are about reaching it. Now, let's journey to one of the most perplexing and downright awkward planets in our solar system, Uranus. While often the subject of schoolboy humor, this ice giant commands serious scientific respect for a feature that is fundamentally, profoundly off-kilter. Every other planet we've studied, from Earth to Jupiter, has a magnetic field that is roughly aligned with its axis of rotation. Think of it like a simple bar magnet running through the planet's core, more or less pointing toward its north and south poles. But Uranus plays by a completely different set of rules. Its magnetic field isn't just tilted a little bit, it's wildly askew, offset by a staggering 59 degrees from its rotational axis. To put that in perspective, if Earth's magnetic field were that tilted, our magnetic North Pole would be located somewhere around Havana, Cuba, instead of in the Arctic. But the strangeness doesn't stop there. Not only is this magnetic field tilted, but its source isn't even at the center of the planet. The magnetic core of Uranus is offset from the planet's geometric center by about a third of the planet's radius. This creates a magnetic field that is lopsided and uneven, a chaotic bubble of magnetic force that is significantly stronger in some areas than others, and it tumbles through space in a completely different orientation than the planet itself spins. This bizarre configuration was one of the major surprises revealed when the Voyager 2 spacecraft flew past in 1986, and it forced scientists to completely rethink how planetary magnetic fields can be generated. The prevailing model for magnetic field generation, known as the dynamo theory, involves the churning motion of electrically conductive fluids in a planet's interior. On Earth, this happens in the molten iron outer core. For the gas giants Jupiter and Saturn, it's thought to occur in a vast layer of metallic hydrogen. Uranus, however, is an ice giant composed mostly of ices like water, ammonia, and methane, but under such immense pressures and temperatures that these substances form a superheated, dense, and electrically conductive fluid. The leading theory to explain the planet's drunken magnetic field points to a very specific and unusual internal structure. Scientists hypothesize that deep within Uranus, the pressures are not high enough to create a solid, Earth-like inner core, nor are the conditions right for a thick, uniform layer of metallic fluid like on Jupiter. Instead, the interior is likely a complex, layered slush. Imagine a vast, deep ocean, but not of water as we know it. This is an ocean of supercritical water and ammonia, packed with dissolved ions that make it an excellent electrical conductor. In this slushy, semi-fluid layer, the motions that generate the magnetic field are not happening in a neat, symmetrical shell around a solid core. the dynamo is likely active in a relatively thin, confined layer within that slushy ocean. Because this layer isn't uniformly thick or centered, and because the convective motions within it are likely chaotic and constrained, the resulting magnetic field it generates is inherently messy, tilted, and off-center. It's as if the planet's magnetic heart is beating from a place that is not its true center, creating a force field that wobbles and staggers through space. This strange internal engine has profound effects on the Uranian system. The lopsided, tumbling magnetic field creates an auroral display that is unlike anything in our solar system. Not neat, concentrated ovals around the poles, but faint, disorganized, and unpredictable glows. It also means that the magnetosphere, the protective bubble formed by the magnetic field that deflects the solar wind, is opening and closing in a chaotic dance as the planet rotates, making it highly unpredictable. This bizarre discovery at Uranus, and a similar one at its sister ice giant Neptune, tells us that the family of planetary magnetic fields is far more diverse than we ever imagined. It's not a one-size-fits-all process. The specific recipe of a planet's interior, its composition, its internal heat, and the precise pressures at different depths can create a magnetic personality that is truly unique, a lopsided wonder spinning in the cold depths of space. If you thought a planet-wide dust storm on Mars was an impressive display of atmospheric power, prepare to meet the true wind champion of our solar system, a world where the very air moves at speeds that defy logic. That brings us to Neptune, the most distant of the Sun's major planets, a brilliant blue marble spinning in the profound cold and darkness of the outer system. At first glance, you might expect this remote ice giant to be a quiet, frozen, and placid world, its weather systems long since calmed by the immense distance from the Sun's warmth. But the reality, as revealed by the Voyager 2 spacecraft during its historic flyby in 1989, is the absolute opposite. Neptune is a cauldron of meteorological fury, a world racked by supersonic winds that scream across its atmosphere at speeds in excess of 1,200 miles per hour. To put that almost incomprehensible velocity into perspective, that is more than 1.5 times the speed of sound here on Earth. A gentle breeze on Neptune would be a catastrophic hypercane on our planet. These are not winds you could stand against. They are a force of nature so immense they would shred any structure into oblivion in an instant. This discovery created a fundamental mystery that planetary scientists are still working to unravel. How can a planet so far from the Sun, receiving only a fraction of 1% of the solar energy that Earth does, possibly generate such ferocious planet-spanning weather? The Sun's heat is the primary engine for atmospheric circulation on Earth, driving our winds and storms, but on Neptune, that external energy source is practically negligible. The answer lies deep within the planet itself. Neptune, unlike Earth, is still actively cooling down from its formation over 4.5 billion years ago. It possesses a tremendous internal heat source, radiating about 2.6 times more energy out into space than it receives from the Sun. This internal furnace is the primary driver of its chaotic weather. As heat from the planet's interior rises through the atmosphere, it creates massive convection currents, like a pot of water boiling on a stove but on a planetary scale. The rising hot gases collide with the frigid upper atmosphere, creating extreme pressure differences that power these incredible wind speeds. Adding to the spectacle are Neptune's colossal storm systems, the most famous of which is the Great Dark Spot. When Voyager 2 gazed upon Neptune, it saw a feature remarkably similar to Jupiter's Great Red Spot, an Earth-sized anticyclonic storm system, a vast, swirling vortex of high pressure roiling in the southern hemisphere. This wasn't a subtle mark, it was a deep blue-black hole in the cloud decks around which the fastest winds on the planet were measured. But here's where the Neptune mystery deepens. When the Hubble Space Telescope later turned its gaze to the ice giant, the Great Dark Spot was gone. It had simply vanished. Subsequent observations have shown that these massive, Earth-swallowing storms periodically erupt on Neptune and then dissipate over a period of just a few years, a rapid cycle of birth and death unlike the centuries-long stability of Jupiter's Great Red Spot. This transient nature suggests that Neptune's atmosphere is even more dynamic and turbulent than we first assumed. The storms likely form when plumes of warm material from the deep interior rise up and punch through the upper cloud layers, creating a massive, stable vortex. But without a stable underlying structure to anchor them, as Jupiter's storm might have, they eventually break apart and fade back into the churning atmosphere. This combination of factors, the supersonic winds powered by internal heat and the fleeting giant storms, paints a picture of a world of breathtaking violence and constant change. Neptune is a stark lesson in not judging a planet by its distance from the Sun. It proves that a world's own internal fire can create a meteorological landscape far more extreme and energetic than anything driven by stellar radiation alone, a howling blue giant reigning over the solar system's frozen frontier. Leaving the howling winds of Neptune far behind, we venture inward into the heart of the asteroid belt, to a world that was long considered little more than a barren, rocky relic. This is Ceres, the largest object in that vast ring of debris between Mars and Jupiter, officially classified as a dwarf planet. For centuries, it was a blurry smudge in our telescopes, and we assumed it was a primitive, frozen time capsule from the solar system's dawn, a place where nothing of consequence had happened for billions of years. That assumption was completely overturned when NASA's Dawn spacecraft arrived in 2015, and its cameras revealed something utterly inexplicable. Scattered across the surface, particularly concentrated within a 57-mile-wide impact basin named Iapetus crater, were dazzlingly bright spots, shining like celestial beacons against the otherwise dark, charcoal-gray landscape. These weren't subtle features, they were brilliant, almost blindingly reflective patches that stood out in stark contrast to their surroundings, creating one of the most captivating puzzles of modern planetary science. The initial speculation ran wild. Some wondered if it could be exposed water ice gleaming in the sunlight. Others, in a more fanciful moment, even joked about alien city lights. The truth, once Dawn's sophisticated instruments analyzed the composition, turned out to be far more interesting and consequential than simple ice. These brilliant spots were vast deposits of salt, specifically a type of sodium carbonate. This is the same kind of salt you might find in a laundry detergent or on Earth in places like the Mono Lake Basin in California. But finding it here on a small, cold world in the asteroid belt was nothing short of revolutionary. Sodium carbonate doesn't just appear on the surface out of nowhere. On Earth, it forms in environments where liquid water has been present, often evaporating and leaving behind concentrated mineral crust. Its presence on Ceres was a giant, flashing neon sign pointing to one undeniable conclusion. This dwarf planet was not dead. It had, and likely still has, a complex internal life involving liquid water. The prevailing theory that has emerged is as fascinating as it is elegant. Scientists believe that the Iapetus crater itself is the key to the entire mystery. The colossal impact that carved out this basin millions of years ago didn't just leave a scar. It fractured Ceres's crust, creating a network of deep cracks and weaknesses that reached down into a hidden layer below. Deep beneath the surface, Ceres is now thought to contain a vast reservoir of briny liquid, a subsurface ocean, or more likely, large pockets of salty mud known as a cryomagma. The impact event effectively punched a hole into this pressurized subterranean sea. This allowed the brine to well up from the depths, seep through the fractures, and erupt onto the cold, airless surface. Once exposed to the vacuum of space, the water in this brine would have quickly sublimated, vanishing as a gas, but it left all of its dissolved salts behind, sprinkling the crater floor and its central dome with a brilliant, reflective coating of pristine sodium carbonate. This process wasn't a one-time event. The incredible detail in Dawn's images shows evidence of multiple episodes of resurfacing and freshening of these salt deposits, suggesting that the briny liquid continued to ooze up long after the initial impact, perhaps driven by the residual heat and pressure from within Ceres. This transforms our understanding of this small world from a static rock into a geologically active, ocean world in its own right. Ceres joins the ranks of Enceladus and Europa as a body with significant subsurface water, but it presents a unique and muddy version of the same theme. The implications for astrobiology are profound. While the surface is now barren and exposed to radiation, that protected subsurface brine reservoir could have provided a stable, liquid water environment for billions of years. It contains not just salts, but also been found to harbor complex organic, carbon-bearing molecules. This means that Ceres possesses the three key ingredients for life: water, essential chemical building blocks, and a long-term source of energy from the decay of radioactive elements in its core or from the chemical reactions between water and rock. It is a dark, salty, subterranean haven that could have been a nursery for probiotic chemistry, or perhaps even simple life. The discovery of Ceres's bright spots fundamentally rewrites the story of the asteroid belt. It is no longer just a junkyard of dry rocks. It contains a complex, evolving dwarf planet that blurs the line between a rocky world and an icy ocean moon. This small, unassuming world has proven that water and geological activity are not exclusive to the outer solar system, and that the potential for habitability can be found in the most unexpected of places, shining brightly for all the universe to see. After exploring the salty secrets of Ceres, we now set our sights on a visitor from the solar system's deepest freeze, a cosmic traveler that revealed its true form to be far stranger than anyone could have predicted. This brings us to number 12 and the European Space Agency's historic Rosetta mission to Comet 67P, Churyumov-Gerasimenko. For years, we pictured comets as relatively simple, potato-shaped dirty snowballs, but when Rosetta finally caught up to its target after a decade-long journey, the world was met with an astonishing sight. There, tumbling through the void, was an object that looked less like a celestial body and more like a child's bath toy, a bizarre, three-dimensional rubber duck composed of two distinct lobes connected by a slender, delicate neck. This was not a single, unified object, but what scientists call a contact binary, two separate chunks of primordial material that had gently collided and stuck together in the early days of the solar system, forming this incredibly peculiar shape. The very existence of this form immediately rewrote the textbook on comet formation. It suggested that the building blocks of comets were not uniform clouds of dust and ice that collapsed into single bodies, but smaller, pre-existing planetesimals that underwent a slow, gentle dance of accretion in the outer darkness, a process more akin to a careful docking maneuver than a violent crash. This gentle merging is why the neck between the two lobes is so fragile. It is littered with house-sized boulders and deep fractures, a testament to its delicate and complex history. As Rosetta spent nearly 2 years orbiting this duck-shaped world, it unveiled one surprise after another. The Philae lander was dispatched to touch down on the surface, a monumental achievement in itself, though its harpoon anchors failed to fire, causing it to bounce and eventually come to rest in a shady crevice. This accident, however, led to another critical discovery. As Philae's instruments analyzed the comet's surface, they found it was not the soft, fluffy layer of dust-covered ice many had anticipated. Instead, the ice was remarkably hard, almost like a solid glacier covered in a thin layer of organic dust. This challenged the classic dirty snowball model, replacing it with a more complex picture of an icy dirt ball, a body with a much higher concentration of rigid, refractory materials than previously thought, with the ice acting as a strong, structural cement holding the entire object together. But perhaps the most profound and unexpected revelation came from the analysis of the comet's coma. the cloud of gas and dust erupting from its surface as it neared the Sun. When the orbiting Rosetta spacecraft sampled this material, it made a detection that left scientists utterly stunned: a significant amount of molecular oxygen. This was a monumental shock. Oxygen is a highly reactive element. It readily bonds with other atoms to form compounds like water or carbon dioxide. Conventional wisdom held that it could not have survived in its pure molecular form for 4.5 billion years in a primitive body like a comet. Its presence meant it must have been frozen into the comet's ices during the very formation of the solar system, trapped in the cold, dark nursery where the comet was born. This forces a complete rethinking of the chemical conditions in the early solar system. It suggests that the primordial cloud of gas and dust from which our planetary system coalesced was much less violent and much colder than we believed, allowing this fragile molecule to be incorporated into the building blocks of comets without being destroyed. The discovery of abundant molecular oxygen on a comet implies that the chemical recipes available for the origins of life might be far more diverse and common than we imagined, as it introduces a key ingredient for metabolic processes in places we never expected to find it. The rubber duck comet 67P taught us that these icy wanderers are not simple, homogeneous relics. They are complex, layered archives, preserving a frozen record of the solar system's birth in their strange shapes and surprising chemistry, reminding us that even the most familiar-looking objects in the cosmos can hold the most extraordinary secrets. An entirely new kind of celestial halo has been revealed around the solar system's largest planet, one that casts an eerie, ethereal glow high above its storm-racked cloud tops. Thanks to the Juno spacecraft's unparalleled polar orbit, scientists have identified a vast, donut-shaped ring of crimson light encircling Jupiter's polar regions, a high-altitude feature formed not from dust or ice, but from ionized hydrogen gas. This isn't a static band of color, it's a dynamic, glowing structure, a veritable river of energized particles caught in a delicate cosmic balance. To understand its origin, we must journey from Jupiter's upper atmosphere all the way to its most volcanically tortured moon, Io. As we explored earlier, Io is a factory of constant eruption, blasting sulfur and oxygen far out into space. This material becomes ionized, stripped of its electrons, and is then swept up by Jupiter's immensely powerful magnetic field. This captured volcanic plume forms a vast, donut-shaped cloud of plasma that follows Io in its orbit, a structure known as the Io-plasma torus. From this torus, the intense magnetic forces channel charged particles down magnetic field lines toward Jupiter's poles, where they slam into the upper atmosphere and spark the most powerful auroras in the solar system, brilliant ultraviolet curtains of light that would dwarf our entire planet. But the story doesn't end there. The same volcanic particles that fuel the auroras also play a crucial role in creating the Crimson Ring. The Juno spacecraft's ultraviolet spectrograph observed that this ring is a signature of ionized hydrogen, but it's glowing at much higher altitudes than the main auroral displays. The leading theory suggests that the volcanoes of Io are, once again, the ultimate suppliers. As sulfur and oxygen from the Io torus are funneled toward the poles, they interact with Jupiter's upper atmosphere in a complex chemical dance. These interactions can actually help liberate hydrogen atoms from molecules like methane or ammonia. Once freed, these hydrogen atoms are then energized by the same violent magnetic processes that create the auroras, causing them to glow with a distinct red hue. This creates a self-reinforcing system. The volcanic junk from Io not only directly powers the brilliant auroral light shows, but it also provides the raw materials and conditions necessary to paint this faint, massive ring in the sky. The Crimson Ring is therefore a secondary effect, an atmospheric echo of the primary volcanic and magnetic fury happening just beneath it. Its delicate, structured nature reveals the invisible architecture of Jupiter's magnetic field lines, tracing out a specific pathway that these energized particles follow. This discovery is far more than just finding a new atmospheric feature. It illuminates the profound interconnectedness of the Jovian system. It shows us that a moon millions of miles away can directly influence the chemistry and appearance of its parent planet's upper atmosphere, creating a glowing, halo-like testament to their gravitational and magnetic bond. This crimson ring stands as a permanent, luminous monument to one of the most extreme relationships in our solar system, a connection forged in volcanic fire and written in light across the polar skies of a giant. Yet another Martian mystery unfolds not on the grand scale of global storms, but in the subtle, seasonal darkening of its steepest slopes. These are the recurring slope lineae, or RSLS, a term that might sound clinical but describes one of the most tantalizing and fiercely debated phenomena in modern planetary science. Imagine looking at the sun-baked walls of a Martian canyon or the rim of a crater. In the warmest seasons, as temperatures climb to a balmy, albeit frigid, -10 degrees Fahrenheit, dark, finger-like streaks begin to appear. They snake their way down the inclines, extending slowly over weeks, sometimes for hundreds of meters, only to fade away when the colder seasons return, then reappear the following year with haunting regularity. When they were first identified in high-resolution images from the Mars Reconnaissance Orbiter, the scientific community was electrified. The explanation seemed almost too good to be true. These looked for all the world like seeps of liquid water, bleeding from the Martian subsurface and trickling downslope in the present day. The initial hypothesis was compelling. Scientists theorized that these RSLS were caused by salty water or brine. The logic was rooted in basic chemistry. Pure water would instantly freeze or boil away in Mars's thin atmosphere and sub-zero temperatures. But if that water was loaded with perchlorate salts, compounds we know exist in the Martian soil, its freezing point would plummet and its ability to evaporate would slow dramatically. This super salty brine could potentially remain liquid long enough to flow downhill, darkening the ground as it went before finally sublimating into the thin air. This wasn't just a geological curiosity, it was a potential bombshell for astrobiology. If liquid water was actively flowing on the surface of Mars today, even in transient, super salty trickles, it would dramatically reshape the search for life. These could be modern-day oases, however temporary and harsh, where microbial organisms might potentially eke out an existence. The possibility sent mission planners into a frenzy, with RSL sites immediately becoming top priority targets for future rovers and strict planetary protection protocols being considered to avoid contaminating these potentially special regions with Earth microbes. But science, in its relentless pursuit of truth, often complicates the most elegant of stories. As researchers looked closer at the RSLS with more powerful instruments and sophisticated models, the water hypothesis began to spring serious leaks. The first major challenge came from orbital spectroscopy. Instruments designed to detect the specific chemical signatures of water, either liquid or in hydrated salts, pointed their sensors at these dark streaks. Again and again, they came up empty. No water signal was detected. If brine was flowing and darkening the soil, it was leaving no discernible spectral fingerprint, which was deeply puzzling. The second, and perhaps more decisive, blow came from a different line of inquiry. A team of scientists began to question whether the flows actually required water at all. They proposed an alternative and decidedly drier mechanism: granular flows. In this model, the driver isn't liquid water, but the sun. As the Martian seasons warm, the angle of sunlight on a steep slope can create just enough of a temperature gradient to destabilize the fine, bone-dry sand and dust grains on the surface. This could trigger small avalanches where darker subsurface material slides downslope, covering the brighter surface dust and creating the dark streaks. The fading occurs when the ubiquitous Martian dust, blown by winds, gradually settles back over the darker material, re-brightening the slope until the next warm season starts the cycle anew. Laboratory experiments on Earth have shown that such dry, granular flows can produce features that look remarkably similar to the RSLS seen in Mars' orbit, complete with their characteristic fingering patterns. Furthermore, detailed analysis of the slopes where RSLS form revealed they are steep enough for dry sand to flow naturally, much like the slumping faces of sand dunes we observe elsewhere on the planet. This dry theory elegantly explains the lack of a water spectral signature and removes the need for a complex and physically challenging mechanism to produce and sustain liquid water in such an unforgiving environment. So, where does this leave the great RSL debate? The truth is, the mystery is far from solved, and the scientific community remains intriguingly divided. It is entirely possible that both processes are at work in different places, or even in conjunction. Perhaps the initial trigger is a tiny, almost undetectable amount of deliquescence, where salts in the soil actively pull minuscule amounts of water vapor from the atmosphere to form a microscopic film of brine on the sand grains. This tiny amount of moisture could be just enough to reduce friction between grains and initiate a flow that then continues as a dry avalanche. This would be a hybrid model where water plays a subtle, facilitating role but is not the dominant component we see from orbit. The enduring enigma of the recurring slope lineae perfectly encapsulates the challenge of exploring another world from hundreds of millions of miles away. We are forced to interpret shadows and colors, to build models based on limited data, and to constantly revise our most cherished assumptions. These dark streaks on Martian slopes are a powerful reminder that the most compelling mysteries are often the most ambiguous ones, the phenomena that refuse to be neatly categorized. They stand as a testament to a Mars that is still dynamically active, a world that continues to change with the seasons, holding on to its most intimate secrets about the presence of the one ingredient we most desperately want to find. Journeying far past the orbit of Neptune into the cold, dark realm of the Kuiper belt, we arrive at a world that was supposed to be a frozen, dead relic, a simple ball of ice and rock where time stood still for billions of years. This was Pluto, the distant dwarf planet, and our preconceived notions of it were utterly dismantled when NASA, a New Horizons spacecraft, shot past in 2015, beaming back images that revealed a world of staggering and unexpected complexity. Among its most breathtaking and perplexing features were colossal mountains that defied all conventional explanation, not jagged peaks thrust upward by tectonic collisions, but what scientists now strongly believe are giant ice volcanoes, a phenomenon known as cryovolcanism. The most prominent of these structures is Right Mons, a towering behemoth that rises over 2.5 miles high and stretches 90 miles across its base. Right next to it lies its slightly larger sibling, Pichard Mons. At first glance, they might resemble the shield volcanoes we see on Earth, like Mauna Loa in Hawaii, with their broad, gently sloping profiles. But there is a profound and fundamental difference. These mountains are not built from layers of hardened basalt lava, but from a frigid, exotic slurry of water ice, likely mixed with ammonia, nitrogen, or methane. Their appearance is bizarre and otherworldly. Right Mons, for instance, features a deep central depression, a summit crater that is not a simple hole but a collapsed caldera. Even more strangely, the flanks of these mountains are not smooth. They are textured with massive, hummocky, blob-like features, as if some thick, viscous slush had oozed out across the landscape in massive globs before freezing solid in the deep space chill. The very existence of such massive structures points to a past, and perhaps even recent, geological upheaval. For a world as small as Pluto to have built mountains of this scale, its interior had to be warm enough to mobilize its frozen contents, pushing them up from below and erupting them onto the surface. This immediately presents a monumental mystery. What could possibly provide the heat to power such activity in a place so far from the sun, where temperatures hover near -400 degrees Fahrenheit? The answer is not a simple one, and it points to a far more dynamic and intricate internal history for Pluto than anyone ever dared to imagine. The leading theory points to heat from the decay of radioactive elements locked within Pluto's rocky core. While this process provides a slow, steady trickle of warmth in many planetary bodies, on its own it was thought to be insufficient to sustain the kind of activity needed to build cryovolcanoes. This has led scientists to consider another, more exotic heat source, an internal ocean. It is now a plausible scenario that Pluto possesses a subsurface ocean of liquid water, kept from freezing by a potent antifreeze like ammonia and insulated by a thick shell of water ice. The heat from the decaying radioactive elements in the core could be enough to maintain this hidden sea. The cryovolcanoes, then, might be the surface expression of this ocean's dynamics. If the subsurface ocean were to partially freeze, the expanding ice could pressurize the remaining liquid, forcing it upward through weaknesses in the overlying icy crust. When this slushy mixture of water, ammonia, and other volatiles reached the surface, it wouldn't explode violently like magma on Earth. Instead, it would slowly and viscously ooze out, piling up layer upon frozen layer to create the massive, domed structures we see today. The presence of ammonia is a key piece of this puzzle, as it dramatically lowers the freezing point of water, allowing it to remain mobile at the incredibly low temperatures of Pluto's interior and surface. The discovery of these potential cryovolcanoes fundamentally shatters our definition of a geologically active world. We once believed that only planets and moons subjected to intense gravitational kneading from a giant neighbor like Io or Europa could exhibit such vibrant geology. Pluto, with no such giant partner to tug on it, has proven that its own internal engine, powered by a combination of radiogenic heat and the unique chemistry of its internal ocean, is potent enough to remodel its surface in dramatic ways, even at the solar system's absolute frontier. It transforms Pluto from a static fossil into a world with a potentially complex thermal history, one that may have experienced episodic eruptions over vast stretches of time. These icy sentinels, Right Mons and Picard Mons, stand as silent, frozen testament to the fact that geological fire is not a privilege of the inner solar system, but a potential that can ignite even in the deepest, darkest cold, forever changing our understanding of what it means for a world to be alive. Far out beyond the orbit of Neptune, in the scattered disk of the Kuiper belt, spins a world that seems to defy the very laws that govern the shapes of planets. This is Haumea, a dwarf planet whose very existence is a testament to a violent and chaotic past. What makes Haumea so immediately bizarre is its shape. We are accustomed to planets and dwarf planets being roughly spherical, their gravity pulling material evenly toward the center. But Haumea is different. It spins with such frantic, dizzying speed, completing a full rotation in less than 4 hours, that its own centrifugal force has stretched it into a distinct ellipsoid. Imagine a piece of clay on a potter's wheel, spun so fast that it flattens and bulges at the middle. Now scale that up to a celestial body hundreds of miles across, and you have Haumea, a cosmic football tumbling through the void. This extreme rotation is thought to be the result of a colossal impact billions of years ago, a glancing blow from another large Kuiper belt object that sent Haumea spinning like a top and also blasted off debris that later coalesced into its 2 known moons, Hiiaka and Namaka. But the strangeness doesn't stop with its shape. Haumea holds an even more peculiar distinction. It is the first dwarf planet ever discovered to possess a ring system. This revelation came not from a visiting spacecraft, but from a precise and elegant astronomical technique known as a stellar occultation. Astronomers carefully predicted when Haumea would pass directly in front of a distant background star, and they trained a network of telescopes across Europe to watch for the star's light to briefly wink out. The data they collected was astonishing. Just before and just after the main body of Haumea blotted out the star's light flickered again, revealing the presence of a narrow, dense ring of material encircling the dwarf planet. The discovery itself was groundbreaking, but the details of this ring system sent theorists back to their drawing boards. This is not a simple, flat disk lying neatly over Haumea's equator like the majestic rings of Saturn. Instead, Haumea's ring is dramatically tilted. It orbits in a plane that is sharply inclined relative to the planet's own equator and, even more puzzlingly, relative to the orbits of its two moons. This configuration presents a profound challenge to our conventional models of how ring systems form and stabilize. Typically, we expect rings to form from debris that is either left over from the planet's formation or generated by the disruption of a moon. In a standard scenario, this debris would naturally settle into the equatorial plane, the zone of gravitational stability where the planet's bulge exerts the most influence. But Haumea's ring stubbornly ignores this rule, occupying its own distinct tilted plane. This forces scientists to consider far more dynamic and complex origins. One compelling theory suggests that the ring is a direct relic of the same ancient impact that spun up the dwarf planet and created its moons. In this model, the collision didn't just eject material that clumped together into moons, it also sent a cloud of fine debris into a range of orbits. Over time, gravitational interactions between this debris, the newly formed moons, and the highly asymmetrical shape of Haumea itself could have forced the debris to settle into a stable, yet tilted, ring plane. The unique gravitational field of a football-shaped world is not uniform. It has complex variations that can trap and shepherd particles into orbits that would be unstable around a perfectly spherical body. This ring acts as a cosmic fossil, preserving the precise orbital dynamics of that long-ago catastrophic event. The tilted ring of Haumea is more than just a curiosity. It is a crucial clue that forces us to expand our understanding of celestial mechanics in exotic environments. It demonstrates that ring systems can exist in configurations we never anticipated, governed by a delicate balance of forces that includes the distinct pull of a rapidly rotating, misshapen world. This discovery opens up the possibility that such tilted rings could be common around other oddly shaped, rapidly spinning objects in the Kuiper belt and beyond, suggesting a hidden diversity of planetary ring architectures that we are only just beginning to uncover. Even on a world already defined by its cryovolcanoes and frozen plains, Pluto had one more breathtakingly strange surprise in store, a geological feature so unique that scientists had to coin a new term for it, the spider-terrain. Scattered across the Tambor Regio region, particularly to the north of the vast, heart-shaped Sputnik planitia, are patterns that look uncannily like colossal arachnids etched into the landscape. Each spider consists of a central depression, a sort of pit, from which dozens of long, straight, and remarkably narrow fractures radiate outward, stretching for dozens of miles in every direction like slender, spindly legs. These are not canyons carved by rivers or cracks formed by simple cooling. They are a complex network of extensional faults, a sign that Pluto's surface is being actively pulled apart. The mechanism that creates this bizarre, sprawling pattern is a fascinating puzzle, and it points to forces at work deep beneath the icy crust. The most compelling explanation involves the slow, monumental upwelling of material from below. Picture the nitrogen ice that forms much of Pluto's surface not as a static, frozen sheet, but as a dynamic, almost plastic layer. Scientists theorize that a plume of warmer, less dense material, perhaps a rising blob of buoyant slush or a surge of warmer ice from the dwarf planet's interior, pushes upward on the overlying crust. This dome-like uplift creates immense stress, stretching the brittle surface nitrogen ice to its breaking point. But instead of cracking in a few random, jagged lines, the ice fractures in this astonishingly organized radial pattern. Think of what happens when you press your thumb into the surface of a frozen puddle. the ice doesn't just crack in one place, it often splinters into a star-shaped pattern of fractures radiating from the point of pressure. The spider-terrain on Pluto is the planetary-scale version of that phenomenon, where a single, persistent upwelling event from below has caused the entire overlying sheet of ice to splinter in a perfectly symmetrical, spider-like fashion. The sheer scale is staggering. Some of these features have dozens of fractures, each one a distinct tectonic feature, all meeting at a single, common center. What makes this process even more intriguing is the role of temperature. Nitrogen ice is unusually soft and malleable, even at Pluto's profoundly low temperatures. As the sun's feeble light provides subtle seasonal changes, the nitrogen ice might be undergoing cycles of expansion and contraction. When a subsurface upwelling adds its own pressure to this system, it could be guiding the resulting stress to release in this specific radial manner. This creates a geological form that is, so far, unique to Pluto in our solar system. We see fractures and grabens on many worlds, from Mars to Mercury, but nowhere else do we find this precise combination of a central uplift and an extensive, radiating fracture system. This tells us that the composition of Pluto's surface, dominated by these peculiar, soft nitrogen ices, is absolutely critical to the formation of such terrain. It's a perfect example of how a specific local recipe of materials, internal heat, and surface conditions can conspire to create a landform found nowhere else. The spider terrain is more than just a geological curiosity. It is a direct window into the ongoing subsurface activity of this distant world. Those sprawling, icy legs are the surface expression of a deep-seated restlessness, a sign that even out in the gravitational quiet of the Kuiper belt, Pluto's internal engine is still running, pushing and reshaping its frozen face in ways that continue to challenge and expand our understanding of planetary geology. While our journey has taken us to frozen plains and methane lakes, we now arrive at a world that represents the absolute antithesis of a winter wonderland, a place where the very concept of snow is turned on its head. Welcome to Venus, a planet so fiercely inhospitable it makes the surface of Mercury seem temperate. Shrouded in a thick, crushing atmosphere of carbon dioxide, with surface temperatures hot enough to melt lead and pressures equivalent to being 3,000 feet deep in an ocean, Venus is a hellscape of staggering proportions. Yet, against all odds, this inferno may host one of the most paradoxical discoveries in the solar system: metallic snow. This isn't the fluffy, water-ice snow we know on Earth. This is a phenomenon born from the planet's extreme vertical climate, a cycle of vaporization and condensation that plays out on a truly alien scale. On the scorching lowland plains, where temperatures rage at nearly 900 degrees Fahrenheit, certain metallic compounds present in the surface rocks don't just melt. They vaporize directly into the lower atmosphere, becoming a metallic mist swirling in the superheated, dense air. But the story takes a bizarre turn when we look upward to the Venusian highlands. The planet features several major mountain ranges like the Maxwell Montes, which tower nearly 7 miles above the mean surface level. As the dense, metallic-laden air is pushed up these colossal slopes by wind, it enters a dramatically different environment. The atmospheric pressure drops significantly, and the temperature, while still brutally hot by our standards, plummets by hundreds of degrees. In these cooler, higher elevations, the vaporized metals can no longer remain in a gaseous state. They condense directly into a solid, settling on the mountain peaks and ridges as a fine, glittering frost. Radar observations from missions like NASA Magellan Orbiter provided the first compelling clues for this phenomenon. The highland plateaus, particularly Maxwell Montes, reflect radar signals with an astonishingly high brightness, far more than the surrounding lowland. This kind of extreme radar reflectivity, or high albedo, is a telltale signature of a smooth, highly conductive surface material. After eliminating other possibilities, scientists were left with a startling conclusion. The most likely candidate for this reflective coating is a layer of metallic minerals precipitated directly from the atmosphere. But what exactly is this snow made of? The exact composition remains a subject of active research, but the leading candidates are as exotic as the process itself. One strong possibility is pyrite, often known as fool's gold on Earth. On Venus, however, its formation would be anything but foolish. In the planet's hot, sulfur-rich, low-oxygen environment, the elements iron and sulfur could readily combine in the atmosphere to form pyrite crystals, which would then settle as a brilliant frost on the high peaks. Another compelling candidate is a mineral called galena, which is lead sulfide. Galena is a semiconductor with exceptional radar reflectivity, and its constituents lead and sulfur are both believed to be present in the Venusian environment. The idea of mountains capped with a frost of lead sulfide perfectly encapsulates the surreal and hostile nature of this world. It's a geological process that mirrors the water cycle on Earth, but reconfigured through a nightmarish high-temperature lens. Instead of water evaporating from oceans, condensing in clouds, and falling as rain or snow, Venus sees metallic elements boiling from the lowland rocks, being transported by global winds and crystallizing on the frigid by Venusian standards mountaintops. This metallic snow is more than just a curious oddity. It's a profound lesson in planetary science. It demonstrates that familiar geological and meteorological cycles can manifest in forms we never imagined, dictated entirely by the unique and extreme conditions of a world. The existence of this phenomenon also suggests that the surface of Venus is far more chemically dynamic and complex than a simple, statically scorching plain. It points to active atmospheric chemistry and a surface that is being subtly but continuously reshaped by these exotic processes, painting the highlands of our sister planet with a bizarre metallic frost that gleams in the perpetual cloudy twilight. Now let's turn our gaze much closer to home, to a world we see almost every night, a place that seems so constant and familiar that its appearance barely changes in our lifetimes. But that constancy is an illusion, and our own moon holds a secret shape hidden in plain sight. You might imagine the moon as a perfect, smooth sphere, a celestial marble floating in the void, but detailed measurements from orbital missions have revealed a startling truth. The moon is not a sphere at all. It is subtly, yet distinctly, lemon-shaped. It possesses solid body tidal bulges, permanent swellings on its surface that make it slightly elongated, as if someone were gently squeezing it at the equator. These aren't the temporary, liquid bulges we see in Earth's oceans, which rise and fall with the tides. These are fossilized high points, enduring distortions in the moon's very crust, and they tell a profound story of a dynamic and fiery past locked in a gravitational embrace with our own planet. The most prominent of these bulges are located on the lines pointing directly toward and away from Earth. Imagine drawing a line from the center of the moon to the center of the Earth. At the 2 points where that line intersects the lunar surface, you would find these ancient raised areas. They are not mountains in the traditional sense, but a broad, continent-scale uplift of the entire landscape, a permanent reminder of a time when the moon was much closer to Earth and far more malleable. The explanation for this bizarre shape lies in the complex dance of gravity and cooling rock. Billions of years ago, shortly after the moon formed from the debris of a giant impact with the early Earth, it was much closer to our planet. The gravitational pull from Earth was immensely stronger than it is today, and the moon itself was still hot and partially molten, its crust only just beginning to solidify. In this primordial state, the Earth's gravity exerted a powerful tidal force, stretching the young, pliable moon. It caused the rock itself to deform, creating 2 bulges, one facing the Earth and one facing away, just as the moon's gravity creates 2 bulges in Earth's oceans. As the moon gradually cooled and its crust thickened and solidified, it began to migrate outward to its present orbit, but the rock once stretched had a kind of memory. The crust effectively froze in that distorted shape, locking the bulges into place as permanent features. It's as if you took a ball of warm, pliable clay, stretched it slightly between your fingers, and then let it cool and harden in that elongated form. That is essentially what happened to the Moon. Its shape is a fossilized snapshot of the extreme gravitational stresses it experienced in its youth. This discovery is far more than a simple geological curiosity. It is a crucial piece of evidence that helps planetary scientists reconstruct the entire tidal history of the Earth-Moon system. By measuring the precise size and shape of these fossil bulges, researchers can work backwards to calculate how much the Moon has receded from Earth over the eons and how quickly its orbit has evolved. It confirms theoretical models that suggest the Moon was once 10 to 15 times closer than it is now, looming enormous in the ancient sky, and that tidal interactions have been the dominant force driving the two worlds apart ever since. This lemon-shaped distortion also has subtle but important effects on the Moon's gravitational field and its internal structure. The bulges represent a slight excess of mass, which can subtly alter the orbits of spacecraft and needs to be accounted for in precise navigation. Furthermore, the existence of these solid tides tells us that the Moon's interior, while largely cold and solid today, must have had just the right combination of rigidity and plasticity in its early history to allow for this permanent deformation to occur. It's a delicate balance. If the early crust had been too rigid, it wouldn't have stretched, and if it had been too liquid, the bulges would have relaxed back into a sphere as the Moon moved away. The fact that we see them today means we are looking at a perfect record of that transitional period in lunar history, a time capsule written not in rock samples but in the very figure of the world itself. Our familiar Moon, a symbol of constancy and romance, is in reality a sculpted relic, its gentle lemon shape a permanent testament to the violent, passionate gravitational tug of war that has defined its existence since the very beginning of the solar system. But if you think the surface of Mars only changes with the seasons, consider a far grander and more gradual kind of transformation, one that involves the entire planet reorienting itself in space over billions of years. This brings us to the evidence for wandering poles on the red planet, a concept that sounds like science fiction but is supported by a wealth of geological data. The idea is known as true polar wander, and it suggests that the geographic north and south poles of Mars have not always been in their current locations. Instead, the entire outer shell of the planet, its crust and mantle, is thought to have slowly slid around, shifting the axis of rotation relative to the surface features, as if the skin of the planet were moving over its core. The clues for this monumental migration are written in the distribution of water ice and in the very orientation of ancient geological formations. Data from orbiters like NASA's a Mars Reconnaissance Orbiter has revealed that there are substantial deposits of water ice located far from the current polar caps, buried in mid-latitude regions where they shouldn't be stable if the planet's spin axis has always been the same. Furthermore, the fossilized remains of ancient glaciers and river valleys seem to align along paths that would only make sense if the planet's climate zones were in completely different positions in the distant past. It's as if you found the remnants of a tropical rainforest in what is now the Arctic. The only logical explanation is that the ground itself has moved. So, what could possibly cause an entire planet to perform such a slow cosmic pirouette? The answer lies in a fundamental principle of physics concerning balance. Any spinning object, from a toy top to a planet, is most stable when its mass is distributed evenly around its axis of rotation. If a significant amount of mass becomes concentrated in one area away from the equator, it creates an imbalance, and the object will naturally wobble as it spins until that excess mass is relocated to the equator, restoring stability. On Mars, scientists have identified the most likely source of this colossal imbalance, the Tharsis volcanic province. This is not just a cluster of volcanoes, it is the largest volcanic structure in the entire solar system, a continent-sized bulge on the Martian surface that is home to the mighty Olympus Mons and the three massive shield volcanoes of the Tharsis Montes. The Tharsis region is so enormous, so incredibly heavy, that its formation over billions of years is believed to have literally tipped the planet over. Imagine spinning a basketball with a heavy lump of clay stuck to one side. The ball would wobble erratically until the clay either fell off or moved to the equator. On a planetary scale, the entire rigid outer shell of Mars is thought to have gradually shifted to bring this immense Tharsis bulge toward the equator, a process that would have moved the geographic poles to new locations relative to the crust. This entire reorientation is a slow-motion geological saga, not a single catastrophic event. It likely occurred in stages over hundreds of millions of years, as massive eruption after massive eruption added more and more material to the Tharsis region, continually upsetting the planet's balance and forcing further adjustments. The evidence for this is etched into the landscape. Researchers have analyzed the positions of ancient, buried water ice deposits and the magnetic signatures locked in the oldest Martian rocks, and they have found that the only model that consistently explains their current locations is one where the poles have wandered by as much as 20 degrees from their original positions. This means that the warm, wet Mars of billions of years ago, with its rivers and lakes, may have had its poles and its tropics in entirely different places than they are today. A region that was once a temperate valley could have slid into a deep freeze, and a former polar desert could have been rotated into a zone where liquid water was stable. This grand reorientation helps solve several long-standing Martian mysteries, such as why some ancient river valleys appear to flow from areas that are now highlands down into basins that are now even higher, defying our standard models of water flow. If the ground itself has moved, then the topography and the climate zones that shaped these features were completely different in the past. The wandering poles of Mars present a breathtaking vision of a dynamic world, one whose very face has slid across the globe over the eons, driven by the awesome, planet-altering power of its own internal geology. Returning to the hazy, hydrocarbon-soaked world of Titan, we find a mystery that plays out not on the grand scale of global geography, but as fleeting, ghostly apparitions on the surfaces of its alien seas. Dubbed the Magic Islands, these enigmatic features were first spotted in radar data from the Cassini spacecraft, appearing as transient, bright patches in the otherwise dark and smooth expanse of Titan's methane lakes like Ligeia Mare. The magic of their name comes from their baffling behavior. They would suddenly appear in one observation pass over the Moon, only to have vanished completely by the time Cassini looked again weeks or months later. They weren't permanent landmasses, they were something far more elusive, phenomena that came and went, leaving scientists to wonder what could possibly be causing such a change on a sea of liquid methane. The very existence of these features points to a dynamic environment, one where the surface of these seas is not static, but actively changing in ways we are only just beginning to understand. One of the most compelling theories to explain these phantom islands involves the concept of floating icebergs, though not made of water ice as we know it. On Titan, where temperatures hover around -290 degrees Fahrenheit, water ice is as hard as bedrock. However, the seas are not made of water. They are primarily a mixture of liquid methane and ethane. Scientists propose that these frigid liquids could allow for a bizarre form of cryovolcanism, or a unique hydrological cycle where other hydrocarbons or even water ice itself could float. Imagine a chunk of solid organic material, perhaps a porous clump of frozen acetylene or benzene, forming on the seafloor or along the shoreline. If this material has a lower density than the surrounding liquid methane, it could break free and bob to the surface, creating a temporary bright radar target, a magic island. After a time, this iceberg might slowly dissolve into the liquid, or perhaps become waterlogged with denser fluid and sink back into the depths, explaining its sudden disappearance. It's a fascinating picture, icebergs not of water but of exotic, complex hydrocarbons, silently drifting across a methane sea under a dim orange sky. Another intriguing possibility is that we are not seeing solid objects at all, but the shimmering surface signature of something rising from below, vast plumes of bubbles. The composition of Titan's seas is complex, and they are likely dissolved with other gases, particularly nitrogen. As seasons change on Titan or as slight shifts in temperature and pressure occur, this dissolved nitrogen could suddenly come out of solution, much like carbon dioxide fizzing out of a soda when you open the bottle. This would create enormous plumes of nitrogen gas bubbling up from the seafloor. When these bubbles break at the surface, they would create a temporary, frothy area that would scatter Cassini's radar signal, making it appear bright. This foamy patch would look like a solid island to the radar, but it would be entirely ephemeral, lasting only until the gas release event subsided and the bubbles dissipated, leaving the sea dark and smooth once more. This theory elegantly connects the Magic Islands to Titan's active climate and geology, suggesting that its seas may periodically fizz with nitrogen, creating a fleeting, effervescent spectacle. A third hypothesis introduces a more radical, wave-based explanation. For a long time, scientists debated whether Titan's low gravity and thick atmosphere would allow for wind-driven waves on its seas. The Magic Islands could be the first indirect evidence that they do exist. In this scenario, the bright radar features aren't objects or bubbles, but the radar reflection off the choppy, textured surface of a wave field. If a gust of wind were to whip up a patch of waves on an otherwise glassy, smooth sea, the radar would see that rough patch as a bright area. When the wind dies down and the waves calm, the bright signature would vanish. This would mean that the Magic Islands are not islands at all, but the ghostly imprint of Titan's weather, the first glimpses of waves on an alien world. The challenge with this theory has been matching the scale and persistence of the observed features with what models predict for Titanian waves, but it remains a powerful contender, painting a picture of a world with not just still lakes, but occasionally wind-swept seas. What makes the mystery of the Magic Islands so compelling is that these explanations are not mutually exclusive. It is entirely possible that all three phenomena, and perhaps others we haven't yet considered, are occurring at different times and in different places. Titan is a world of immense chemical complexity, and its seas are likely active, bubbling, and sloshing with processes we are only beginning to model. The transient nature of these features tells us that Cassini merely provided a fleeting glimpse of Titan's dynamic surface processes. A future mission, like the proposed Dragonfly rotorcraft, won't be landing on the seas, but its observations from the air could help solve this puzzle by providing long-term monitoring of how these lakes and seas change with the seasons. The Magic Islands are a perfect example of how a single, curious observation can open up a universe of possibilities, reminding us that even the seemingly placid surfaces of other worlds are alive with secret, shifting activity. Hovering just 3,700 miles above the rust-colored plains of Mars is a moon that seems to defy both logic and gravity. This is Phobos, a lumpy, potato-shaped world so small you could walk its entire circumference in a single day, and its surface is etched with one of the most visually arresting and fiercely debated mysteries in our solar system. From a distance, Phobos looks like it has been meticulously raked by a cosmic gardener. Its face is scarred by a vast network of parallel grooves, long, linear trenches that run side by side across the landscape, creating a pattern of stripes that is both beautiful and deeply puzzling. These grooves are not subtle features. Some are hundreds of meters long, tens of meters wide, and they slice straight across impact craters and other geological formations, as if they were drawn on the surface long after the moon's major features were already in place. When the first clear images of these grooves were beamed back from orbiting spacecraft, scientists were immediately captivated. What kind of force could create such a uniform, systematic pattern on a world that is barely held together by its own meager gravity? The debate over their origin has split planetary scientists into two main camps, each with a compelling but fundamentally different story to tell about the violent life and eventual death of this tiny moon. One of the most dramatic and widely discussed theories suggests that the grooves are not surface features at all, but the outward expression of a world being slowly torn apart from within. Phobos orbits incredibly close to Mars, so close that it whips around the planet faster than Mars rotates, rising in the west and setting in the east in a matter of hours. This intimate dance subjects the moon to an immense and relentless tidal pull from the immense gravity of Mars. Just as our own moon's gravity stretches Earth's oceans to create tides, Mars's gravity exerts a profound stretching force on the body of Phobos. This theory posits that the entire moon is under immense tidal stress and that these parallel grooves are essentially stretch marks, the surface manifestation of deep-seated fractures in the moon's interior. As Phobos continues its slow, inward spiral toward Mars, pulled closer by tidal interactions over millions of years, these stresses are only increasing. In this view, the grooves are the first cracks in the foundation, the early signs of a future cataclysm where the tidal forces will finally overcome the moon's own structural integrity, ripping Phobos apart to form a temporary ring of debris around the red planet. The uniformity of the grooves, all running roughly parallel, fits with the idea of a systematic global stress field where the moon is being pulled apart along predictable fault lines. It's a breathtakingly grim prognosis for this small world, turning its entire surface into a preview of its own inevitable destruction. The opposing theory, however, offers a completely different narrative, one that looks not to the future demise of Phobos, but to the violent past of its parent planet. This hypothesis suggests that the grooves have nothing to do with internal fractures, but are instead chains of secondary impact craters. Imagine a massive asteroid slamming into the surface of Mars with such unimaginable force that it blasts enormous plumes of Martian rock and soil high into space, far above the planet's gravitational grasp. Some of this ejected material would go into orbit around Mars, and a significant portion of it would eventually cross the orbital path of the unsuspecting Phobos. Because Phobos is so small and has such a weak gravitational field, it cannot pull this material in from a great distance. Instead, the debris would essentially rain down upon the moon in a series of nearly parallel streams, with each individual rock or boulder striking the surface in a tight, linear sequence. Each impact in the chain would create a small crater, and when viewed from above, these crater chains would appear as continuous grooves. This model elegantly explains why the grooves appear to radiate from a single point on Phobos, the giant Stickney crater, a colossal impact basin so large it nearly shattered the moon. A titanic impact that created Stickney could have easily generated enough ejected material to seed the entire Martian system with debris, which then subsequently bombarded Phobos, carving the grooved patterns we see today. In this scenario, the grooves are not a sign of the future, but a fossilized record of a single, catastrophic event in the Martian system's history. Each of these theories has its own strengths and its own perplexing weaknesses. The tidal fracture model powerfully explains the global, systematic nature of the grooves and their alignment with the tidal forces exerted by Mars. However, detailed computer simulations sometimes struggle to show how such clean, surface-breaking fractures could form without completely disrupting the moon's weak, rubble pile interior. The impact chain theory, on the other hand, has the advantage of a clear and dramatic mechanism, and we see similar, though smaller, cratered chains on our own moon. The challenge for this theory is explaining the remarkable uniformity and distribution of the grooves across the entire surface of Phobos. It requires a bombardment event of just the right intensity and direction to create such a perfect pattern. The truth may, as it often does in planetary science, lie somewhere in the middle. Perhaps the initial grooves were formed by the secondary impacts from the Stickney event, and those ancient wounds have since been reactivated and widened by the ongoing tidal stresses, creating the deep, crisp features we observe today. This hybrid model suggests that Phobos is a world caught in a double bind, simultaneously bearing the scars of an ancient cataclysm while being slowly pulled apart by the planet it circles. The urgency to solve this mystery is not merely academic. Phobos is a prime target for future space missions, including potential sample return efforts and even human landings, as it could serve as a strategic outpost for exploring Mars. Understanding whether its surface is stable or fracturing apart is a critical question for mission safety. Landing a spacecraft on a world that is actively cracking under tidal stress would be a perilous endeavor. Furthermore, if the grooves are indeed chains of Martian material, then a mission to Phobos becomes a mission to Mars by proxy. The surface of this small moon could be littered with rocks blasted from different eras of Martian history, offering a free and easily accessible collection of samples from all over the red planet without ever having to land on its surface and launch back off. The grooves of Phobos, therefore, are more than just strange lines on a small moon. They are a Rosetta Stone for understanding the relationship between Mars and its satellites, a record of cosmic violence, and a crucial puzzle that must be solved before we take our next steps into the deeper reaches of our celestial neighborhood. While we often associate auroras with planets, our next discovery proves that even a moon can put on a spectacular light show, provided it has the right kind of secret. At number 23, we travel to Ganymede, Jupiter's largest moon, and a world so massive it dwarfs the planet Mercury. This colossal moon doesn't just have a complex, grooved surface of ice and rock. It also possesses something utterly unique in the solar system, its own auroras. Imagine standing on the frozen, fractured plains of Ganymede, looking up at a sky dominated by the colossal banded sphere of Jupiter. In that sky, you would witness shimmering curtains of light, similar to our own northern lights, but with a crucial and telling difference. These are not powered directly by the solar wind, as they are on Earth, but by a complex and relentless electrical circuit generated by Jupiter's own monstrous magnetic field. Ganymede is the only moon we know of that generates its own intrinsic magnetic field, a protective bubble created by a churning, molten iron core. This creates an extraordinary situation where the moon's small magnetic field is embedded within the overwhelming, gargantuan magnetic field of its parent planet. As Jupiter's magnetic field sweeps past Ganymede, it interacts with this smaller field, stretching and compressing it, and in the process funnels energetic charged particles down toward the moon's polar regions. When these particles slam into the thin, oxygen-based atmosphere that surrounds Ganymede, they excite the atoms and cause them to glow, creating the beautiful, ethereal auroral ovals that we can observe from Earth orbit. The existence of these auroras was fascinating enough, but it was their subtle, peculiar behavior that led to one of the most brilliant indirect discoveries in modern astronomy. For years, scientists using the Hubble Space Telescope carefully monitored the rhythmic rocking of Ganymede's auroral ovals. As Jupiter rotates, its immense magnetic field shifts, and this should cause Ganymede's auroras to sway back and forth in a predictable clockwork pattern. Yet the observations revealed something was off. The auroras weren't rocking as much as they should have been. They were subdued, their motion dampened, as if some invisible hand was holding them in place, resisting the powerful tug of Jupiter's magnetic influence. This tiny anomaly was the key that unlocked a world-spanning secret. The only force powerful enough to counteract the influence of Jupiter's magnetic field in this way is the magnetic field generated by another electrically conductive material. And the most plausible candidate for that material, sloshing beneath Ganymede's icy crust, is a vast global ocean of salty water. Here's how this elegant detective story works. A saltwater ocean is an excellent conductor of electricity. As Jupiter's changing magnetic field sweeps over Ganymede, it doesn't just affect the moon's core. it also induces a secondary magnetic field within the subsurface ocean itself. This induced field, generated by electrical currents flowing in the salty water, pushes back against Jupiter's field. Think of it like electromagnetic friction. This counteraction works to stabilize Ganymede's own magnetic field, reducing the amount of sway in the auroras. By meticulously measuring the precise amount of damping in the auroral rocking, scientists were able to calculate the strength of this secondary magnetic field and from that deduce the properties of the hidden ocean. The data pointed to a staggering reality. Buried beneath about 100 miles of ice, Ganymede harbors a saltwater ocean that contains more water than all of Earth's oceans combined. This ocean is likely sandwiched between layers of ice, with a top layer of familiar water ice and a bottom layer of exotic, dense ice forms created by the immense pressure. The discovery was a masterstroke of indirect observation. We didn't need to drill through the ice or land on the surface to confirm the ocean's existence. We simply watched the lights in the sky. This method of using magnetic fields to probe for hidden oceans has since become a cornerstone of planetary science, a powerful tool for uncovering the secrets of other icy worlds. Ganymede's subdued auroras are far more than a beautiful phenomenon. They are a luminous dial, a cosmic gauge that we learn to read, and in doing so, we uncovered the presence of a vast dark sea, a hidden abyss on a moon that is now one of the most promising places in our entire solar system to search for environments capable of supporting life. As our countdown nears its conclusion, we arrive at one of the most visually iconic and scientifically profound discoveries from the outer solar system: the great beating heart of Pluto. When the New Horizons spacecraft revealed its first stunning images of the dwarf planet, one feature dominated the landscape: Tombaugh Regio, a vast heart-shaped plain of dazzlingly bright nitrogen ice that instantly captured the world's imagination. This was not just a charming geological coincidence. It turned out to be the primary engine driving Pluto's entire climate system, a dynamic force that controls the weather on a global scale and orchestrates a beautiful, complex cycle of ice transport across the dwarf planet's surface. The western half of this heart, an enormous basin called Sputnik Planitia, is the crucial component. It's a deep, smooth plain, predominantly filled with a thick slab of solid nitrogen, along with smaller amounts of carbon monoxide and methane ice. This massive, bright reservoir acts like a colossal thermal capacitor, but its influence extends far beyond simply storing cold. Because of its unique composition and topography, Sputnik Planitia becomes the dominant cold trap on Pluto, a region where atmospheric gases preferentially freeze out of the thin air and accumulate as surface ice. This process sets up a remarkable atmospheric feedback loop that governs the dwarf planet's winds and its seasonal rhythms. The mechanism hinges on a simple but powerful principle: the sublimation and deposition of volatile ices. When Pluto's distant sun shines on the nitrogen ice in Sputnik Planitia, even its feeble light provides enough energy to cause some of the solid nitrogen to turn directly into a gas, a process called sublimation. This release of gas adds to Pluto's tenuous atmosphere. However, the sheer mass of the ice in the basin creates a localized cold spot. The air above Sputnik Planitia is significantly colder and denser than the atmosphere over the rest of the planet. This density difference creates a constant, gentle downhill flow of air, as if the atmosphere were a fluid seeking its own level. Dense, cold air from above the heart basin slides down and outward along the surface, pushing lighter, warmer air upward in other regions. This establishes a persistent global circulation pattern that is unique in our solar system. Unlike Earth, where our weather is driven by solar heating and the planet's rotation, Pluto's winds are primarily dictated by the chilling presence of its own icy heart. The nitrogen that sublimates from Sputnik Planitia is then carried aloft by these very winds, transported around the globe until it eventually encounters a cold enough surface to freeze out once again, completing the cycle. This isn't a random process. The heart effectively breathes its atmosphere in and out over the course of Pluto's long seasons, which last for nearly 250 Earth years, redistributing its icy skin in a slow, cosmic rhythm. This cycle of ice transport carves and reshapes Pluto's entire landscape in dramatic ways. The winds flowing out from Sputnik Planitia carry fine particles of nitrogen ice, which act like a slow-moving sandblaster, scouring the surfaces of distant mountain ranges and carving the remarkable blade-like terrain observed in the Tartarus Dorsa region. These dark, aligned ridges, which look like the scales of a giant cosmic dragon, are thought to be massive dunes of methane ice or erosion-resistant spines shaped by the persistent, wind-driven deposition and erosion of nitrogen frost. The constant redistribution of ices also explains the stark contrasts across Pluto. The heart remains brilliantly white because it is the primary cold trap, continuously collecting fresh frost, while darker, redder regions of Tholen's complex organic molecules created when methane is irradiated by the sun are left exposed in areas where the nitrogen ice is stripped away by the winds or fails to accumulate. This creates a planet with a face of two distinct characters, one half dominated by the bright, youthful plains of the heart, and the other by ancient, cratered, and darkly stained terrain. The heart of Pluto is therefore far more than a static landmark. It is an active planetary scale pump, a climate control center that uses its own frozen body to drive the winds, shape the geology, and paint the surface of a world we once thought would be geologically inert. It's a stunning demonstration of how a single, dominant feature can hold sway over an entire planetary environment, a beautiful and complex dance of ice, atmosphere, and gravity that continues to reshape this distant, fascinating world. And so we reach the final discovery on our list, one that carries us beyond the familiar boundaries of our own solar system and into the vast ocean of interstellar space. In October 2017, astronomers in Hawaii detected a faint point of light moving at a speed so staggering it could not possibly be bound by the sun's gravity. This was no ordinary comet or asteroid from our own celestial backyard. It was the first confirmed interstellar visitor ever observed, an emissary from another star system passing through our neighborhood. It was given the name Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. From the moment it was spotted, it was clear this object was unlike anything we had ever seen. Its path was hyperbolically curved, a trajectory that meant it was merely cutting through our solar system on its way to some other, unknown destination in the galaxy. As telescopes around the world swiveled to track this cosmic tourist, the initial data revealed its first major peculiarity, its shape. By measuring how its brightness changed dramatically as it tumbled end over end, scientists deduced that Oumuamua was not a roughly spherical or lumpy rock. Instead, it was profoundly elongated, with a shape best described as a pancake or a cigar, estimated to be up to 10 times longer than it was wide. These extreme proportions are unlike any known asteroid or comet in our solar system, making it a truly alien form tumbling through the void. The strangeness only deepened as researchers continued to analyze its motion. As Oumuamua sped away from the sun, something was happening that defied the simple, predictable laws of gravity. Its trajectory was ever so slightly off. It was accelerating in a way that could not be explained by the gravitational pull of the sun or the planets. It was experiencing what scientists call a non-gravitational acceleration. For comets, this is a common occurrence caused by the rocket-like effect of volatile ices like water vaporizing on the sun-warmed surface and jetting out into space, creating a visible coma and tail. But Oumuamua displayed no such coma, no tail, no visible outgassing whatsoever. It appeared as a completely inert, rocky object in every observation, yet it was behaving as if it had a hidden engine. This paradox ignited a firestorm of scientific debate and public fascination. What unseen force was pushing this mysterious visitor along? the leading natural explanation, developed after intense scrutiny, involves a mechanism known as hydrogen outgassing. The theory suggests that Oumuamua could be a cosmic iceberg composed largely of molecular hydrogen ice. This exotic substance could form in the cold, dense cores of giant molecular clouds in interstellar space. As the object made its close pass by the Sun, the solar radiation would have heated it, causing the solid hydrogen to sublimate directly into a gas. Because hydrogen is very difficult to detect with our telescopes, this outgassing could have provided the necessary push for the observed acceleration without producing a visible coma. It would be like a stealth comet venting an invisible propellant. Another compelling natural hypothesis posits that Oumuamua is a shard from a larger planetary body, specifically a Pluto-like world or an exo-Pluto from another star system. In this scenario, the object could be composed largely of nitrogen ice, much like the heart of Pluto's Sputnik Planitia. A violent impact or a close encounter with its parent star could have shattered this distant dwarf planet, ejecting a fragment of its frozen nitrogen crust into the interstellar void. As this nitrogen ice shard traveled for millions or billions of years through space, it would have been eroded by cosmic radiation, sculpting it into its bizarrely flattened shape. The non-gravitational acceleration could then be explained by the sublimation of this nitrogen ice as it was warmed by the Sun, again providing a thrust without the dusty signature of a typical cometary tail. This theory elegantly connects Oumuamua to the kind of worlds we are only just beginning to understand in our own solar system, suggesting that the processes that created Pluto's strange geology might be common throughout the galaxy. Of course, the most sensational and controversial theory came from Harvard astronomer Avi Loeb, who famously raised the possibility, however slim, that Oumuamua could be a piece of advanced alien technology, a light sail or a derelict spacecraft. Proponents of this idea pointed to the object's unusual shape, which would be aerodynamically stable for an interstellar probe, and the fact that its non-gravitational acceleration was remarkably smooth, as if it were being pushed evenly across its entire surface, consistent with the effect of radiation pressure from starlight on a thin, light sail. While this captivating idea captured the public imagination, the overwhelming majority of the scientific community maintains that an extraordinary claim requires extraordinary evidence, and that the natural explanations, while still being refined, are far more probable. The intense debate surrounding Oumuamua's true nature, from hydrogen iceberg to planetary fragment, is a testament to just how unexpected and challenging this first interstellar visitor was. It forced astronomers to confront the limits of their knowledge and to develop new, creative models to explain its bizarre properties. The legacy of Oumuamua is not a single, definitive answer, but a profound shift in our perspective. Its visit demonstrated that interstellar objects are not just theoretical constructs, they are real, and they are passing through our solar system with some frequency. It has spurred new plans for missions to intercept the next such visitor, equipped with instruments designed to unravel its secrets up close. Oumuamua, this silent, tumbling enigma from the depths of interstellar space, serves as the perfect conclusion to our journey through the solar system's bizarre discoveries. It is a humbling reminder that for every mystery we solve, the universe presents us with a dozen more, and that the greatest wonders are often those that arrive unannounced from the great, unexplored dark. From the screaming winds of Neptune to the silent, drifting enigma of Oumuamua, these 25 discoveries are far more than a simple list of curiosities. They are a collective declaration of how little we truly know about our own cosmic neighborhood. Each one, from Saturn's perfect hexagon to the potential icebergs floating in Titan's alien seas, serves as a stunning reminder that our solar system is not a static, well-mapped museum. It is a vibrant, dynamic, and often bewildering arena where the laws of physics conspire to create realities more fantastical than any fiction. We have witnessed worlds with subsurface oceans holding more water than all of Earth's seas combined, planets that are actively shrinking, and dwarf planets capped with ice volcanoes that spew a frigid, muddy slush. We have found moons that are tearing themselves apart, others that are painting their parent planets with ethereal rings of light, and entire landscapes that are in constant, slow-motion conversation with hidden realms below. This is not the orderly, predictable solar system you learned about in grade school. This is a place of profound mystery where the familiar is a thin veil over the utterly alien. The very fact that so many of these discoveries have been made not in the distant past, but within our own lifetimes by missions like Cassini, New Horizons, and Juno, tells us something crucial. We are living in the golden age of exploration. Every time we send a new robotic emissary into the void or point a more powerful telescope at the sky, we are virtually guaranteed to find something that completely upends our expectations. The old models are crumbling, and in their place, a new, more complex and infinitely more exciting picture is emerging. One of active geology in the coldest reaches, of hidden oceans in the most unlikely places, and of chemical processes we are only beginning to comprehend. This is the true legacy of these 25 bizarre finds. They are not in points but starting points. Each answered question immediately gives rise to a dozen new, more profound ones. Does life swim in the dark abyss of Europa's ocean? What drives the supersonic winds on an ice-cold world like Neptune? Is the surface of Pluto's heart still actively renewing itself? These are the mysteries that now drive us forward, the puzzles that will inspire the next generation of scientists, engineers, and explorers. So the next time you find yourself under a clear night sky, take a moment to really look. Gaze at the steady glow of Jupiter, the faint ruby dot of Mars, or the delicate crescent of Venus, but do not see them as mere points of light. See them for what they truly are, entire worlds, each with its own unique and often bizarre story, each a frontier waiting to be understood. Let that sight rekindle the innate human drive for discovery that has always propelled us to seek what lies beyond the next hill, across the next ocean, and now out among the planets. The greatest discoveries are not behind us, they are waiting, hidden in the data streams of current missions and in the plans for voyages not yet launched. The solar system has shown us its strange and wonderful hand, and the game is far from over. Stay curious, keep looking up, and remember that the next great revelation, the one that will once again rewrite all the textbooks, is always just